Welcome back to the Deep Dive. Today we're cutting through the noise, focusing on a really groundbreaking research report. It's titled Quantum Computing: How Will It Impact AI? And this analysis comes straight from Morgan Stanley's Global Technology Foundation. It's hot off the press, published just June 26, 2025. Now, for you, our listeners, this isn't just tech news. The implications for Wall Street are huge. It really sets the stage for the next decade.
Absolutely. And the report's message, it's crystal clear. Quantum computing isn't just, some lab experiment anymore. It's fast becoming a core pillar for AI's next evolution. It's designed to work with classical computing, not replace it. And the potential disruption across business domains, immense. We are genuinely talking about a quantum leap beyond the Silicon Age we know.
Okay, let's unpack this, maybe for those of us without a quantum physics degree handy. What is the fundamental shift? How is quantum computing different from classical? And why does AI specifically need this?
Right. The core difference is how information gets processed. Classical computers use bits, zeros or ones, simple on-off switch, quantum chips. Well, they tap into quantum mechanics using qubits. Now, these qubits, they can be in multiple states at the same time. That's called superposition. This lets them run an exponential number of calculations simultaneously. It just blows classical supercomputers away in terms of speed for certain problems.
So not just on or off, but kind of everywhere in between, doing many things at once, like a dimmer switch.
Exactly. That's a decent analogy. And then you've got entanglement. Qubits get linked. They share information instantly, no matter how far apart. It's weird, but powerful. Think of two linked coins, always landing the same, instantly. That connection allows for incredibly complex processing. And one more key thing. Quantum computation is probabilistic.
Probabilistic, meaning not always a single right answer.
Sort of. You get a probability distribution of possible answers, so you often need multiple runs to zero in on the most likely accurate result. But these runs happen at light speed, effectively, so the overall power is enormous.
Okay, so connecting this back to AI then. Is quantum a competitor to our current AI models? Or is it more like a partnership?
Oh, definitely a partnership, a powerful synergy. Quantum computing augments AI. It doesn't compete head-to-head across the board. Think of quantum chips as specialized accelerators. Quantum accelerators for AI systems, they unlock things classical computing just can't touch. Current AI is great at creativity, language, video, that stays. But quantum, it tackles the really complex stuff. Optimization problems, boosting power efficiency, advanced machine learning tasks that stump classical methods.
And you mentioned power efficiency. That's a huge issue with current large AI models, right? The energy consumption.
Exactly. That's a really critical point. Quantum models might need fewer parameters, less energy. Imagine making AI more sustainable. That's a massive potential benefit, addressing a huge long-term challenge for the whole industry.
Okay, this is where it gets really interesting for our listeners. It's not theory, it's a global race. Capital is flowing. So where are we with commercial viability? And who's leading? Which companies, which nations are making the big moves?
Well, we're still in the very early innings. The market was only about $500 million in 2024. But the projections, they're staggering. US $22 billion by 2030. Maybe US $1.3 trillion by 2035. That's not just growth, that's a hockey stick curve. A massive shift is coming. For Wall Street, this isn't some far-off thing. It's about figuring out where that initial $22 billion lands and how to position for the trillion-dollar jump within, 10 years.
And a timeline for actual use.
The consensus seems to be around 2029, 2030 for meaningful commercial applications. And critically, you mentioned security earlier, there's this looming Q-Day, NIST, that's the U.S. National Institute of Standards and Technology. They've put a timeline around 2030 for needing quantum secure algorithms, because quantum could break current encryption.
Q-Day, 2030. That sounds dramatic, almost like a deadline for digital security. How should, say, financial institutions prepare? And who are the players driving this?
It is dramatic, and preparation is vital, especially for finance, healthcare, anywhere with sensitive data. Existing encryption, it could become vulnerable, very vulnerable. That's why there's such a push for PQC, post-quantum cryptography. It's urgent. As for who's leading, the U.S. is definitely out front right now in hardware and algorithms. Look at IBM. They're arguably the overall leader. 75-plus system installations already. They're aiming for an error-tolerant quantum computer by 2029, and their software, Qiskit, most used quantum platform globally.
Error-tolerant by 2029. That sounds ambitious.
It is, but look at their roadmap. They're talking systems like Starling by 2029, 100 million quantum operations, 200 logical qubits. Then Blue Jay by 2033, a billion operations, 2,000 logical qubits. That's serious scale. And importantly, IBM has actually hit their roadmap targets consistently since 2019. That track record matters, gives credibility.
Okay, IBM's a giant. What about Google, Microsoft, Amazon? How are they playing this? Different angles?
Yeah, definitely different angles, pushing different boundaries. Google's Willow chip, 105 qubits, made a big splash with exponential quantum error reduction. Error reduction is maybe the key challenge right now. These systems are so noisy, so fragile, reducing errors exponentially. That's a potential game changer for making quantum practical and, frankly, affordable. Google showed calculations done in minutes that take supercomputers, well, basically forever. 10 septillion years, they claimed. Their quantum AI director thinks practical apps are maybe 5 years out.
And Microsoft.
Microsoft's betting on something called topological qubits with their Majorana 1 chip. These are different. The quantum information is kind of woven into the structure of the material itself. The idea is they're inherently more stable, less prone to noise, which could be a path to scaling up massively, maybe 1 million qubits on one chip eventually. It's a different path to stability.
1 million qubits, wow. And Amazon.
Amazon came out with their Ocelot chip just this February. It uses something called hat qubits. The main claim is reducing the cost of error correction by up to 90%. Again, hitting that crucial error problem, but from a cost angle. Plus, their Amazon Bracket service is already a major cloud platform for researchers to access various quantum hardware. Focus on access.
So IBM, Google, Microsoft, Amazon. Are these different approaches, like topological versus error reduction, competing directly, or are they all just trying to solve the puzzle different ways? And are there other key U.S. players?
I'd say they're largely complementary. Everyone's tackling fundamental challenges: stability, errors, scale, integration. It's not zero-sum yet. And yes, beyond the big hyperscalers, you have companies like IonQ. They lead in trapped ion qubits. Another modality. They just bought Oxford Ionics, strengthening their position. Their roadmap targets 800 logical qubits by 2027. IonQ is also pushing into quantum networking. They supported the first commercial quantum network in the U.S.
Networking. Interesting. What about NVIDIA? They're huge in AI hardware now.
Right. NVIDIA's approach is different again. They're not building the quantum processors themselves mostly. They're focused on accelerated quantum supercomputing. Basically, integrating quantum processors with their existing AI supercomputers. Think GPUs plus QPUs. Their CUDA-Q platform and research center aim to be the bridge, the enabling software and integration layer.
In Europe, you mentioned Quantinuum.
Yes, Quantinuum. That's a Honeywell joint venture, a big player based in the UK. They're aiming to set the standard for software with TreeKit and Nexus OS. And they had a major breakthrough with Microsoft, demonstrating thousands of error-free operations using reliable logical qubits. That showed real progress towards practicality.
Okay, so strong U.S. and European efforts. But you mentioned China earlier. How did their approach fit in? And does the report touch on risks from these different national strategies, like tech decoupling?
It does, and that's a key geopolitical angle. China is a major force, especially in quantum communication and networking. They actually lead there. They have a massive 12,000-kilometer quantum network built out, and their Zhuchongzi 3 processor, 105 qubits, claim it speeds vastly faster than classical supercomputers. But their approach is very different. It's highly centralized, government-funded. Remember that U.S. $138 billion venture fund launched in March? That's state backing on a huge scale. This contrast, U.S. private sector drive versus China's state-led push, absolutely could fuel competition, affect supply chains, maybe even lead to diverging tech ecosystems. It's a big watch item.
Beyond the U.S., Europe, and China, any other regions we should keep an eye on?
Definitely. The UK has its $1 billion national quantum strategy, strong research working closely with the US. South Korea is ambitious. They want 1,000 qubit computers by the 2030s, aiming for 10% of the global market by 2035. You've got major Korean companies like LG, Samsung involved in PQC algorithms, SK Telecom in quantum communication. Australia has a national quantum strategy too, projecting a $6 billion industry by 2045, significant government funding. And Japan's Moonshot Goal 6 aims for fault-tolerant universal quantum computers by 2050. NTT already has a photonics-based quantum computer on the cloud. It's truly global.
Wow. Okay, so switching gears slightly. What about the ecosystem? The supply chain needed to build all this. Is it like semiconductors or totally different? And then let's nail down the practical applications for industries. What does this mean for your business or investments?
The supply chain is fascinating and, yes, very distinct from standard semiconductors. That creates unique challenges and opportunities. Hardware first. Chip fabrication is highly specialized specialized. Companies like Rigetti, Skywater, Angstrom, they're the quantum foundries, dealing with exotic physics. Then you need special packaging for noise reduction, extreme cooling near absolute zero. Companies like FormFactor, Bluefors are key there. And even specialized wiring for the microwave signals to control the qubits, like from Zurich Instruments. These aren't household names, but they're critical bottlenecks and potential investment points. Understanding this niche supply chain is vital.
And the software side?
Software is largely quantum as a service, QCAs, mostly cloud-based. Projected market around $770 million by 2030, but growing fast. You have system software, IBM's Qiskit, Quantinuum's Tkit, the operating systems essentially, and application software like from QCware trying to build usable programs. But here's a key challenge to report flags. We still lack truly killer quantum algorithms that fully exploit the hardware. There's huge white space there for innovation.
Okay, applications. Let's get concrete. Which industries see the biggest impact? Give us examples.
The potential impact is broad, really transformative across sectors. First, optimization. Think beyond just routing trucks better. Imagine global supply chains that react instantly to disruptions, weather, politics, whatever. Saving billions, boosting resilience for multinationals. That's quantum optimization.
Okay.
What else? Material science. This is huge. Not just discovering drugs faster, but designing entirely new materials with specific properties from the atoms up. Think super efficient batteries, better catalysts for industry, revolutionary materials. It could spawn entirely new product categories.
Finance.
Big implications. Better risk analysis, portfolio optimization that sees connections classical models miss, faster, more nuanced market insights, and of course, highly secure communication for transactions using quantum principles.
You mentioned security before, the double-edged sword. Breaking encryption, but also enabling new security.
Exactly. Shor's algorithm is the threat to current encryption, but quantum also enables unbreakable communication. Quantum key distribution, QKD, makes eavesdropping physically detectable. Quantum random number generators, QRNGs, provide true randomness for stronger keys. And look at Samsung, they already put a PQC, a post-quantum crypto solution, in their Galaxy S25 phone. This isn't science fiction. It's hitting consumer products now, aligning with that NIST 2030 timeline.
Amazing. One more area?
Sensing and metrology, enhanced imaging for self-driving cars maybe, better medical diagnostics, environmental monitoring with incredible precision, or spotting tiny defects in semiconductor manufacturing, even GPS-free quantum positioning systems, QPS, for defense or navigation where GPS fails or is jammed, unparalleled precision.
Okay, the potential is staggering. But let's talk reality check. What are the core investment implications for our listeners? And the biggest risks? It sounds like high reward, but high risk too.
Absolutely. Huge growth potential, no doubt. But the risks are equally significant because the tech is still so nascent. A smart approach probably involves diversified exposure. Look across the supply chain, not just the quantum computer makers. Include those critical component suppliers, the software platforms, maybe early application developers, and differentiate. Pure-play quantum startups. Higher risk, higher potential reward maybe. Big tech companies integrating quantum. Potentially a more stable, diversified bet.
And the specific risks.
Number one is probably the uncertain time to market. Are we 7 years away from scaled error-corrected systems? Or 15? Nobody knows for sure. 2, capital requirements. Building these things is incredibly expensive. Intense competition for funding and for scarce talent. 3, economic sensitivity. Long R&D cycles are vulnerable to downturns. 4, supply chain bottlenecks for those specialized parts. 5, regulations are still evolving. And 6, the constant risk of technological obsolescence. A breakthrough by one company could make another's approach obsolete overnight. So definitely a long-term strategic play, not for quick flips.
Right.
Makes sense.
So to wrap this up, what does this all mean for you? Let's leave you with a few provocative questions based on everything we've discussed.
Okay, first question. We know quantum isn't replacing classical computers, it's complementing them for specific, super complex tasks. So how should your business strategically split R&D? How much goes to advancing classical AI versus investing in these nascent quantum capabilities to get ahead over the next decade?
Good one. Second, we see very different national approaches. The U.S. leads in hardware, driven by the private sector. China leads in quantum communication, driven by the state. How might these different paths shape the geopolitical tech race? And what does that mean for global collaboration or supply chain security?
And finally, third question. If quantum does drastically cut the energy and cost of AI training, reducing reliance on today's power-hungry GPUs, what strategic moves should major tech and financial firms make today? Think harvest now, decrypt later. How do you prepare for or even capitalize on that potential shift in computing paradigms?
The future here isn't about one winner. It looks more like a complex symphony combining the super fast, the super smart, and the super secure. We definitely encourage you to explore these possibilities further.